At the dawn of an era that redefined the limits of human engineering, when the sky ceased to be merely a dream and became an operational reality, humanity faced a challenge that seemed insurmountable. It was the beginning of the 1940s, and the world was undergoing a period of great transformation and urgency. While aviation was developing rapidly, a crucial technical challenge presented itself in the skies, where the thin air and freezing temperatures created a formidable natural obstacle. The fighter planes of that era were magnificent machines, the result of years of development and innovation. However, there was an insurmountable limit that haunted every engineer, every pilot, every military commander who dared to look to the sky. This limit was not imposed by man, but by nature itself. At 12,000 meters of altitude, where oxygen is scarce and temperatures plummet to 50 degrees below zero, conventional engines simply ceased to function properly. And it was in this scenario of apparent impossibility that one of the most extraordinary stories in military aviation began. Imagine for a moment sitting in the cramped cockpit of a fighter jet, spiraling through the clouds on an intercept mission. The engine roars under the cowl, vibrating through the entire aluminum and steel structure. You climb 5,000 meters, then 8,000, then 10,000. The air gets thinner and thinner, your breathing becomes difficult even with the oxygen mask, and then you realize something worrying. The engine starts to fail. Power drops drastically. The plane that once climbed with agility now struggles to gain every meter of altitude. And up there, far above you, another aircraft continues its course, unreachable because its engines were designed to work where yours cannot. This was the reality faced by American pilots in the early 1940s. While they watched other aircraft operating efficiently at seemingly impossible altitudes, frustration gripped the squadrons. It wasn't just a technical disadvantage. It was an issue that profoundly impacted the operational capabilities of aviation. Before we continue this extraordinary journey through the history of aviation, I'd like to ask you to subscribe to the channel and leave a comment saying what time you're watching this video. Your participation helps keep the memory of these incredible achievements of human engineering alive. To fully understand how we arrived at this critical point, we need to go back a few years, to the late 1930s, when military aviation was still in its infancy compared to what it would become just a few years later. The piston engines that powered the aircraft of that time were essentially improved versions of the engines used in land automobiles. They operated on the same basic principle, internal combustion, where a mixture of air and fuel is compressed and then ignited, generating the force that moves the pistons and, consequently, the propellers. However, these engines had a fundamental and inescapable dependence on the oxygen present in the air. For every liter of gasoline burned, the engine needed approximately 15 liters of air. At sea level, where atmospheric pressure is higher and the air is denser, this poses no problem. The engine naturally draws in the necessary air through the movement of the pistons. But as an airplane climbs, the story changes completely. For every 1,000 meters of altitude gained, atmospheric pressure decreases by about 11%. This means that the air becomes progressively less dense, containing fewer oxygen molecules per unit volume. At 5,000 meters, the pressure is approximately half that found at sea level. At 12,000 meters, the pressure is only a quarter. And this is where the problem becomes critical, because without sufficient oxygen, combustion becomes inefficient, incomplete, and weak. The engine loses power drastically, sometimes losing more than 60% of its capacity. The first aviators to explore high altitudes discovered this through hard experience. There are records of pilots from the 1910s and 1920s who attempted to climb beyond usual limits, only to see their engines sputter and fail, forcing them to descend rapidly before they completely lost control of their aircraft. During the years between the Great World Wars, as civil aviation began to develop and transcontinental routes became a reality, engineers realized they would need to find a solution to this problem if they wanted airplanes to fly higher, faster, and more efficiently. The first attempts to solve the altitude problem were, to say the least, rudimentary. Some engineers simply experimented with increasing the size of the engines, thinking that more cylinders and greater capacity would solve the issue. Others tried modifying the compression ratio, adjusting the ignition timing, or even using different types of higher-octane fuel. But all these solutions offered only marginal improvements. the fundamental problem remained. The rarefied air did not provide enough oxygen for efficient combustion, regardless of how many modifications were made to the engine itself. It was then that an idea emerged that would completely change the landscape of high-altitude aviation. If the problem was the lack of dense air at high altitudes, why not bring dense air along with the aircraft? Or even better, why not force more air into the engine, artificially compressing it before it entered the cylinders? This simple but revolutionary idea gave rise to two devices that would become fundamental to modern military aviation: the turbocharger and the supercharger. To understand how these devices work, imagine trying to inflate a balloon in a room where the air is very thin. You would blow and blow, but the balloon would barely fill up. Now imagine having a pump that compresses the air before you blow into it. Suddenly, the balloon fills up easily. Turbochargers and superchargers do exactly that with the air entering the engine. They compress it, increasing its density and therefore the amount of oxygen available for combustion. The mechanical supercharger was the first solution developed. It consisted of an air pump driven directly by the engine via gears or belts. While the engine was running, some of its energy was used to rotate the supercharger, which in turn compressed the air before injecting it into the cylinders. The idea was elegant in its simplicity, but it had a significant drawback. Because the supercharger was mechanically driven by the engine itself, it consumed a considerable percentage of the engine's power output. It was like pedaling a bicycle while carrying extra weight. You would reach your destination, but you would expend much more energy in the process. The turbocharger, on the other hand, was a more ingenious solution. Instead of using the engine's mechanical energy directly, it harnessed something that would normally be wasted: the exhaust gases. When the engine burns fuel, the resulting gases are expelled through the exhaust pipes at high temperature and pressure. These gases contain considerable energy that, in most conventional engines, simply dissipates into the atmosphere. The turbocharger captures this energy using a turbine placed in the path of the exhaust gases. These high-speed gases cause the turbine to spin rapidly, and this turbine is connected via a shaft to a compressor that forces air into the engine. It was essentially recycling wasted energy to solve the problem of altitude. But this is where the story becomes both fascinating and frustrating. Because although the theory behind turbochargers was well understood by the late 1910s, and functional prototypes had existed since the 1920s, transforming this technology into something reliable and efficient enough for military use proved extraordinarily difficult. The challenges were immense and multifaceted. First, there was the issue of temperature. The exhaust gases from an aircraft engine can reach temperatures exceeding 800 degrees Celsius. The turbocharger turbine had to operate continuously at these extreme temperatures without deforming, cracking, or failing. The materials available at the time could barely withstand these conditions. Existing metal alloys either melted or lost their structural strength when subjected to intense heat for extended periods. Finding materials that could withstand not only the heat but also the mechanical stresses of rotating at speeds exceeding 100,000 revolutions per minute was a problem that kept engineers awake at night. Then there was the issue of regulation. A turbocharger needs to supply the right amount of compressed air to the engine under all flight conditions. At sea level, where the air is already dense, little or no pressure increase is needed. But at 12,000 meters, the turbocharger needs to compress the air several times to compensate for altitude. This means the system needs sophisticated controls that automatically adjust the amount of compression based on altitude, engine speed, and several other factors. And all of this had to work perfectly during pilot operations, including complex maneuvers, climbing and descending rapidly. There was also the problem of lubrication. The bearings that supported the high-speed shaft of the turbocharger needed constant lubrication, but the conventional oils of the time did not perform well in the extreme temperatures found in a turbocharger. At very high temperatures, the oil chemically decomposed, losing its lubricating properties and forming carbon deposits that could seize the mechanism. At very low temperatures, common at high altitudes, the oil became too viscous, increasing friction and reducing efficiency. And we can't forget the problem of detonation. When you compress air, it heats up. That's a fundamental law of thermodynamics. The air coming out of the turbocharger can be significantly hotter than the ambient air, sometimes 50 degrees or more hotter. When this hot air enters the engine and is compressed again by the pistons, the temperatures can become so high that the fuel detonates prematurely, before the spark plug ignites it. This premature detonation, known as knocking, can destroy an engine in a matter of minutes, melting pistons and damaging cylinders. Throughout the 1930s, as tensions grew internationally, American engineers worked intensely to solve these problems. General Electric, which had pioneered the development of turbochargers since the 1920s, led the efforts. Its facilities in Lynn, Massachusetts, became the nerve center of turbocharger research. Hundreds of engineers, metallurgists, chemists, and technicians worked in shifts, testing materials, developing new designs, failing, learning, and trying again. The tests were exhaustive and dangerous. Engines were mounted on special benches and operated continuously for hours, sometimes days, while instruments recorded every imaginable parameter. Temperatures, pressures, rotational speeds, fuel consumption, everything was measured, analyzed, compared. When an engine failed, and they frequently did, teams of engineers disassembled each component, examining it under microscopes, searching for clues about what had gone wrong. It was meticulous, frustrating, but absolutely essential work. Meanwhile, other engineers were working on the problem of intercoolers or air coolers. These devices were special radiators placed between the turbocharger and the engine, designed to cool the compressed air before it entered the cylinders. The concept was simple. Pass hot air through an array of thin tubes surrounded by cooler air, allowing the heat to dissipate. The cooled air would be denser and less prone to causing detonation. But implementing this in a fighter jet was anything but simple. Intercoolers added weight, complexity, and created aerodynamic drag. Every cubic centimeter of space in a fighter jet was precious, and finding room for an efficient intercooler was a constant puzzle for the designers. Meanwhile, across the Atlantic, British and German engineers were following slightly different paths. The British, with their long tradition at Rolls-Royce and other aircraft engine manufacturers, focused more on multi-stage mechanical superchargers. Their famous Merlin engines, which would power the Spitfires and Hurricanes, used increasingly sophisticated superchargers. The Germans, in turn, were developing both superchargers and turbochargers, but faced many of the same challenges as the Americans. And then came December 1941, when historic events definitively brought the United States onto the global stage. Suddenly, the development of high-altitude engines ceased to be merely an interesting research project and became an urgent national priority. The American government invested unprecedented resources in the program. New facilities were built, thousands of additional engineers were recruited, and deadlines that had previously been measured in years were now measured in months. The first months of 1942 presented significant challenges. American fighter planes, even the latest models, proved inadequate for high-altitude operations. There were reports of American pilots attempting to reach operational altitudes, only to discover that their aircraft simply could not reach the necessary altitude, or if they could, they had so little power remaining that they were unable to maneuver effectively. One of the most notorious cases of this technical necessity occurred when aircraft were operating at high altitudes. Planes flying at over 12,000 meters operated with apparent ease at these extreme altitudes. When other fighters tried to catch up, they discovered that their engines barely functioned at that height. Climb speeds dropped drastically. Maneuverability was severely compromised. It was a clear technological disadvantage. It was in this context of technical urgency that the first significant advances finally began to appear. General Electric, working in close collaboration with the United States Army Air Force, developed a new generation of turbochargers that incorporated all the hard-won lessons of previous years. New materials, developed specifically for high-temperature applications, allowed the turbines to operate reliably even under extreme conditions. More sophisticated control systems, using early examples of automatic feedback mechanisms, dynamically adjusted the compression pressure based on flight conditions. Simultaneously, advances in petroleum chemistry led to the development of aviation fuels with much higher octane ratings. These new fuels could withstand higher pressures and temperatures without premature detonation, allowing engines to operate at higher compression ratios and therefore generate more power. Lubricating oils were also revolutionized. New synthetic additives allowed oils to maintain their properties over a much wider temperature range. But perhaps the most crucial advance was in the integrated design of systems. Engineers realized that it wasn't enough to have an efficient turbocharger, or a good intercooler or high-quality fuel. All these components needed to work together as a harmonious system. This required a completely new approach to aircraft design, where the engine, the turbocharger, the cooling systems, and even the aircraft fuselage were designed simultaneously, taking into account the complex interactions between all these elements. The result of this intensive collaboration between engineers, chemists, metallurgists, and aircraft designers began to appear in factories in late 1942 and early 1943. New fighter models began to be produced, equipped with engines that incorporated all this revolutionary technology. The Republic P-47 Thunderbolt was one of the first and most successful examples. This massive aircraft, nicknamed Jug by its pilots due to its robust shape, was equipped with a Pratt & Whitney R-2800 radial engine coupled to a General Electric turbocharger. The result was impressive, with more than 2,000 horsepower available even at 12,000 meters of altitude. When the first P-47s arrived in the operating areas, the impact was immediate and significant. Pilots who previously faced limitations in reaching high altitudes now discovered that they could not only reach them, but operate with speed and maneuverability. The Thunderbolt could climb to altitudes that previously presented great challenges, and once there, it had more than enough power for its operations. There were extraordinary stories of pilots who, for the first time, felt confident in high-altitude operations. One pilot described the experience of flying at almost 15,000 meters. With his engine operating smoothly even at that extreme altitude, he was able to perform complex maneuvers, demonstrating the technological advancement achieved. But turbocharger technology wasn't limited to fighter jets. Bombers also benefited enormously. The Boeing B-17 Flying Fortress and the consolidated B-24 Liberator, the main American heavy bombers, were equipped with turbochargers in all their engines. This allowed them to perform operations at significant altitudes, demonstrating the versatility of the technology developed. As 1943 progressed into 1944, American technological superiority in high-altitude engines became increasingly pronounced. Mass production of turbochargers had been mastered, with thousands of units being manufactured monthly. The reliability problems that had plagued early models were largely resolved. Pilots learned to operate these complex systems efficiently, understanding the nuances of controlling compression pressure, managing temperatures, and keeping the engines operating within their ideal parameters. There were also parallel developments that complemented turbocharging technology. Water methanol injection systems were developed to further cool the air-fuel mixture during periods of maximum power. When activated, these systems injected a mixture of water and methanol into the engine intake, causing a dramatic drop in temperature through evaporation. This allowed the engine to operate at even higher compression pressure without risk of detonation, providing a temporary but significant boost in available power, extremely useful during intense operation or in situations demanding maximum performance. Control systems also became increasingly sophisticated. Early turbochargers required the pilot to manually adjust various controls, balancing compression pressure with engine speed, altitude, and other factors. It was a task that demanded constant attention and considerable experience. But later models incorporated automatic controls that made most of these adjustments without pilot intervention. A pilot could focus on flying their aircraft and performing their operations, while the turbocharger automatically adjusted to deliver optimal power in all conditions. The American aviation industry had learned valuable lessons about mass production during this period. The techniques developed to manufacture thousands of airplanes quickly were also applied to the production of turbochargers and other engine components. Manufacturing tolerances were standardized. Quality control processes were implemented. Technicians were trained on a large scale. The result was an impressive production capacity for turbocharged airplanes. But we cannot tell this story without mentioning the men who flew these machines. The pilots who soared into the skies day after day, entrusting their lives not only to their skills, but to the complex engineering that kept their engines running at altitudes where the air was so thin that breathing was impossible without assistance. where temperatures were so low that exposure for even a few minutes would be fatal. These men developed a profound respect for the technology that kept them alive. There were rituals that pilots developed before each flight. They would walk around their planes, visually checking every component. They would touch the turbocharger, feeling if it was cold or if there were signs of oil leaks. They would check the fuel lines, the controls, the instruments. It was more than a standard procedure. It was a way of connecting with the machine that would soon be taking them to altitudes where the slightest mechanical failure could be fatal. During flight, pilots constantly monitored their instruments. Compression pressure, oil temperature, cylinder head temperature, everything had to be within the correct parameters. Any deviation could indicate an imminent problem. There were stories of pilots who noticed small anomalies in their instruments and aborted flights, only to discover later that their turbochargers were about to fail. This constant vigilance, this intimate knowledge of how their engines should sound and feel, saved countless lives. As the year 1945 approached, technological advancements in aviation were remarkable. Airplanes were flying at altitudes that would have been impossible without turbocharging technology. The ability to operate effectively at high altitudes had been achieved through years of intense development. When peace finally arrived, the aviation industry did not forget the lessons learned during those intense years of development. Turbocharging technology, refined under the pressure of the needs of the time, became standard in post-war civil aviation. Commercial airlines that began to expand rapidly in the 1950s used aircraft equipped with turbochargers or superchargers, allowing them to fly higher, faster, and more efficiently. Jet engines, which began to appear in the late 1940s, also benefited from the knowledge gained. Although jets operate on different principles than piston engines, they also need to compress air, and many of the techniques developed for turbochargers were applied to the design of jet engine compressors. High-temperature metal alloys, sophisticated control systems, precision manufacturing processes, all of these found application in the new era of jet aviation. But perhaps the most important legacy of this era is not merely technological. It was a powerful demonstration of what human engineering can achieve when faced with seemingly impossible challenges. In the early 1940s, effectively flying at 12,000 meters seemed as impossible as flying to the moon. But through hard work, perseverance, creativity, and collaboration, engineers transformed the impossible into routine in less than 5 years. Today, when we fly comfortably in commercial airplanes at 11 or 12,000 meters of altitude, we rarely think about the extraordinary technology that makes this possible. The engines that propel us through the skies are direct descendants of those developed in that crucial era. They incorporate decades of refinement and improvement, but the fundamental principles remain the same. Each modern engine is a testament to the ingenuity of those engineers who worked tirelessly to solve the problem of altitude. It's fascinating to consider how a specific technical challenge led to advancements that have benefited all of humanity. The need for aircraft capable of operating at high altitudes not only represented a technological milestone but also opened the skies to modern commercial aviation. Millions of people travel the world every day, connecting cultures, facilitating business, reuniting families, all made possible because engineers 80 years ago refused to accept that skies above 12,000 meters were inaccessible. The history of high-altitude engines also teaches us about the importance of fundamental research. Many of the advances that made turbochargers practical came from research in seemingly unrelated fields. New materials developed for other applications found use in turbines. Advances in petroleum chemistry, initially aimed at other industries, proved crucial for aviation fuels. Precision manufacturing techniques developed for the automotive industry were adapted for aeronautical production. It is a reminder that knowledge is interconnected, and that investing in broad research often leads to benefits in unexpected areas. There are also lessons about collaboration. The successful development of high-altitude engines was not the work of a single brilliant inventor or a single company. It was the result of collaboration between multiple organizations: engine manufacturers, turbocharger manufacturers, oil companies, metallurgical companies, universities, and government agencies. Each organization brought its unique expertise, and only by working together could they solve such a complex problem. And we cannot forget the role of testing and iteration. Early turbochargers failed repeatedly. Engines exploded on test benches. Prototypes disintegrated in flight. But each failure taught something. Each problem identified led to an improved design. Engineers did not give up after the first failures or the 10th or even the 100th. They persisted, learned, adapted, and eventually triumphed. It is a lesson about the importance of resilience and the willingness to learn from mistakes. When we look at the legacy of this era, we see not only technological advancements but also human impact. Thousands of pilots benefited from the technology that enabled safe high-altitude operations. The technology developed represented a qualitative leap in safety and operational capability, benefiting not only military aviation but also laying the foundation for the modern commercial aviation we all know today. In modern aviation, we continue to push the boundaries of what is possible. Airplanes fly higher and faster than the pioneers of the 1940s could have imagined. But the principles remain. The challenge of providing sufficient oxygen for combustion at high altitude still exists, and the solutions still involve forced air compression, whether through turbochargers, superchargers, or the multi-stage compressors of modern jet engines. There is something profoundly inspiring in understanding that the apparent limits of nature are not absolute. The thin air at high altitude is a physical reality that cannot be changed, but our response to that reality can be transformed through ingenuity. When faced with an obstacle, we have choices. We can accept the limit and work within it, or we can develop technology that allows us to transcend it. The story of high-altitude engines is a story about choosing the second option. As we conclude this journey through one of aviation's most transformative eras, it's important to remember that every great technological achievement is built on the shoulders of countless individuals whose names may never be known. For every famous engineer whose name appears in history books, there were hundreds of technicians, machine operators, metallurgists, chemists, and factory workers whose contributions were equally essential. They toiled long hours in harsh conditions, often without recognition, driven by the conviction that their work made a difference. And indeed it did. The world we inhabit today, where traveling between continents is a matter of hours instead of weeks, where global business is conducted face-to-face, where students can study in distant countries and return home regularly, this world is only possible because of the work of those pioneers. They weren't just developing engines. They were building the foundations of a globalized and interconnected world. As we look to the future, we face new challenges in aviation. The need to reduce emissions, to make flight more sustainable, to develop new forms of propulsion that are environmentally responsible. These challenges are as daunting as the altitude problem was in the 1940s. But history teaches us that seemingly impossible challenges can be overcome through dedication, creativity, and hard work. Today's engineers carry on the legacy of those who came before. They work with more advanced tools, powerful computers, sophisticated simulations, and materials their predecessors could not have imagined. But the spirit is the same. A refusal to accept limitations as absolute. A belief that solutions exist if we search diligently enough. And a willingness to fail, learn, and try again. This story of high-altitude engines is, ultimately, a story about humanity's capacity for adaptation and overcoming challenges. When confronted with a sky that seemed impenetrable above a certain altitude, we did not accept this limitation. We developed technology to transcend it, and in doing so, we opened up possibilities that transformed the world and laid the foundations of modern aviation. May we always remember this lesson as we face the challenges of our own time. May we have the courage to question apparent limits. May we have the creativity to imagine solutions that do not yet exist. May we have the perseverance to continue working even when progress seems impossible. And may we have the wisdom to work together, combining our talents and knowledge to achieve what none of us could achieve alone. May the Lord God bless us in all our pursuits of knowledge and progress, illuminating our paths with His divine wisdom.